It is Crystal here, and this video, what we're going to be talking about is sampling distributions, and we're going to be using R to gain a greater understanding of those distributions. So a sampling distribution is the probability distribution of a given statistic based on a large number of samples drawn from the same population. It describes the distribution of a statistic, e.g. sample mean, sample variance, that results from repeated sampling of the population. The concept of a sampling distribution is rooted in the understanding that different samples from the same population can yield different statistics due to random variability. So, in the last video, we discussed types of sampling techniques that you can use, and the different sampling techniques that you can use will yield different sampling distributions. So now what we're going to talk about in this video is applications of sampling distributions. And the first application that we're going to be talking about is the sampling distribution of the sample mean. And the mean, you calculate the mean by you take the number of elements in a sample and you add up all the elements in the sample and you divide that by the number of elements in the sample, and that's going to give you the mean. So we've got a demonstration of that, and what we're going to do is we're going to create this sampling distribution of the sample mean in R for you so you can see how it works. So the first thing we want to do is we want to set our seed, which is set.seed brackets 1, 2, 3. And then we're going to create a skewed population, which is going to be an exponential distribution. So population becomes Rx. That means it's going to be randomly selecting from an exponential distribution. Brackets 100,000, comma, rate equals 1 over 10. So basically what you have is you have a mean of 10 in this exponential distribution. And then we're going to draw repeated samples and compute the sample mean. So N becomes 30. So that's going to be how many samples you're going to select. Sorry, I got that wrong. N equals 30, and the number of samples is 5,000. So the sample mean becomes replicate, brackets, num samples, comma, mean, brackets, sample population, sample brackets, population, comma, N, comma, replace equals true. So we're going to plot the sample distribution with a histogram. So you've got hist bracket sample means, comma, col is your color equals sky blue, comma, main, that's your title equals sampling distribution of the sample mean, comma, xlab, that's your label for your x-axis is sample mean, and freq, that's your frequency, equals false. And then we're going to add a normal curve for comparison. So curve brackets d norm, so that's letting you know it's a normal curve, brackets x, comma, mean equals mean bracket sample mean brackets, comma, SD, that's your standard deviation, equals SD bracket sample means, comma, col equals red, that's your color, LWD, that's your line width, equals 2, and add equals true. So now what we're going to do is we're going to plot this, the sample mean of the sampling distribution of the sample mean. So you can see that the actual curve is very similar to the distribution. And the distribution, because it was an exponential distribution that we have created, so that means that it's skewed, and it's going to be skewed to the right. It doesn't tell you that skewed to the right in the code, but when you look at it, you can see that the distribution is skewed slightly to the right. So this is the sampling distribution of the sample mean. Also, it proves the central limit theorem, which we're going to also cover in this video. And the central limit theorem states that you can take any distribution, and if it's a large distribution, and any distribution, and if you sample it enough times, then the samples of the distribution will form a close to a normal distribution. So you can see here that although we have used an exponential distribution, which I believe is skewed to the right, when we have sampled it enough times, the distribution itself resembles a normal distribution, even though it was originally an exponential distribution. So the next thing we're going to do is we're going to perform a hypothesis test of a sampling distribution. So the first thing we want to do is we want to set our seed at, and what happens when you set your seed is every time you run this cell, it's going to set the variables up to the same values. So set.seed brackets 1, 2, 3, mu 0 becomes 50, and that's your mean. Sigma becomes 10, that's your standard deviation, and n becomes 30, and your number of samples is 5,000, which is similar to what we had in the previous cell, because in the previous cell n was 30 and the number of samples was 5,000. So we're going to create a sampling distribution of the sample mean under HO. And HO is your null hypothesis. And so what happens under a null hypothesis? Null hypothesis means that the difference, the sample mean and the difference between the two means. So like the population mean and the sample mean, there's no significant difference between the two means that you are testing, because you're always going to have one mean. You're always going to have like one mean and then another mean that you're going to compare it to. And the null hypothesis means there's no significant difference between the two means that you are testing. And so that's what we're going to be looking for. So null dist becomes R norm. So that's going to be randomly selected normal distribution, brackets, num samples, comma, mean equals mu 0, comma, SD equals sigma, and that's your standard deviation, divided by square root of n. And then we're gonna create the observed mean. So x bar obs becomes 53.2. So that's your observed mean. So the population mean, I believe, the population mean is 50, or that's mu. That's the mean that you're setting it at. But your observed mean is 53.2. So we're going to plot the sampling distribution of this by creating a histogram. So no hist brackets, no dist, comma, breaks equals 40, comma, call, that's your color, equals light blue, comma, frequency equals false, comma, main, that's your title, sampling distribution of the sample mean under HO, xlab equals sample mean. And then we're going to add a theoretical normal curve brackets d norm, that's the normal distribution, brackets x, comma, mean equals mu, comma, SD equals sigma, divided by square root of n, comma, color equals red, comma, line width equals 2, comma, add equals true. And then we're going to add the observed sample mean, AB line. That's where we're creating a line in the graph. Brackets, V equals X bar obs, comma, col equals dark green, comma, line width equals 3. And then we're going to compute the p-value. So p-value becomes mean, brackets, ABS, brackets, null dist minus mu is greater than or equal to abs, that's your absolute value, brackets, X bar obs minus mu. And then we're going to print the p-value, and the p-value is going to be 0.788. 1 second. So we calculated the p-value is 0.788. And if you've watched my previous videos, your p-value is, if the p-value is greater than 0.05, then that means you fail to reject the null hypothesis. And so since the p-value is greater than 0.05, we have failed to reject the null hypothesis. And then we're going to shade the rejection region. As X vowels becomes SEQ, that's a sequence, brackets, min, brackets, null dist, comma, max, brackets, null disk, comma, length equals 500. So it's going to be from the minimum value to the maximum value of the null distribution. Y vowels becomes d-norm, that's a normal distribution, brackets, X vowels, comma, mean equals mu, comma, SD equals sigma divided by square root of n. So now we're going to create our left tail and polygon, brackets, C, brackets, min, brackets, X vowels, comma, X vowels, square brackets, X vowels less than or equal to mu minus a absolute value of X bar minus mu, bracket, square brackets, comma, mu minus absolute values of X bar obs minus mu, comma, C, and that means you're creating a vector, you're combining these values, brackets, 0, comma, Y val, comma, square brackets, X val is less than or equal to mu minus absolute value, brackets, X bar obs minus mu, square brackets, comma, 0, brackets, comma, color equals RGB, brackets, 1000.4, brackets, border equals NA. And then you do the right tail, which is similar to the left tail with a little bit of change in coding. So polygon, brackets, C, brackets, mu, plus absolute value, brackets, X bar obs minus mu, comma, X vowels, square brackets, X vowels is greater than or equal to mu, plus absolute value of X bar obs minus mu, bracket, square brackets, comma, max, brackets, X vowels, so that's the maximum value of the X vowels, brackets, comma, C, so we're creating another vector, bracket, 0, comma, Y vowels, square brackets, X vowels greater than or equal to mu, plus absolute value of brackets, X bar obs minus mu, square brackets, comma, 0, brackets, comma, color equals RGB, brackets 1000.4, and border is NA. So this is what we have plotted. So you can see the mean is 50 because the mean of the population is 50. So that's actually the center of the graph. And the observed mean is 53.2, which is just right at the edge of the rejection region. And then you can see you've got the rejection region on the right hand and the left hand of the histogram, and you see that we've got a kernel density estimate curve, a normal distribution curve on the graph as well. So we plotted what we have created. So the next thing we're going to do is we're going to prove the central limit theorem. And basically what the central limit theorem states is for any distribution, if it is sufficiently large, if you take enough samples, the distribution of the samples that you have taken will resemble a normal distribution. And so what we're going to do is we're going to prove the central limit theorem in a cell using R. And you're going to be covering central limit theorem over and over and over in your statistical studies. So the first thing that you want to do is you want to set your seed. So set dot seed brackets 1, 2, 3. So what that happens is every time you run this cell, the variables are going to set up to initialize to the same values. So we're going to create a uniform distribution. And so R pop, that's your population, R pop becomes a function, brackets N, and then run if, brackets N, comma, N equals 0, max equals 1. So you're going to create a uniform distribution from 0 to 1. And then a uniform distribution is where all the values are pretty much the same. And so the distribution actually looks like a rectangle when you look at it. So we're going to set our settings. The number of samples is 5,000, which we have used in the previous two cells. The number in values becomes C. It's creating a vector of brackets 1, 2, 5, 10, 30. So what we're going to do is we're going to sample this uniform distribution 1 time, 2 times, 5 times, 10 times, and 30 times. And so par brackets M fro equals C brackets 2, 3. So what you're going to do is you're going to have 2 rows with 3 columns of plots, and then we're going to create a fourth loop so that we can sample this uniform distribution through n values. So for n values, and then so we've created this for loop, and we're going to generate the sampling distribution of the mean. So sample means becomes replicate brackets num samples, comma, mean brackets r pop brackets n. And then we're going to create a histogram of the means. So hist brackets sample means, comma, breaks equals 30, comma, frequency equals false, comma, color equals light blue, comma, main equals paste brackets n equals n. So because what happens is we're going to be creating a histogram for every time each number of samples. XLab, that's your X label, equals sample mean, and XLM equals C bracket 0 to 1. So your X limits are 0 to 1. So we're going to create a theoretical central limit theorem normal curve. So mu becomes 0.5. So that's the mean of the uniform distribution of 0.0 to 1. Sigma, that's your standard deviation, becomes 1 divided by 12. that's a variance of uniform 0, 1. But sigma is supposed to be standard deviation. But anyway, SE is your standard error, becomes square root of brackets sigma 2 divided by n. So that's your standard error. And then we're going to create a curve in each histogram. So curve brackets d norm, the curve is going to be based on a normal distribution, brackets x, comma, mean equals mu, comma, SD equals SE. So they're taking the standard deviation as the standard error. That's not quite true, but that's what they're making it. Comma, color equals red, comma, line width equals 2, comma, add equals true. And then so what we're going to do now is we're going to add text to the chart. It says central limit theorem, uniform 0, 1, plus sampling distribution of the mean. And it says outer equals true, line equals -2, CEX equals 1 to 1. So we're going to have 5 different samples. And the reason why we're going to have five different charts, and the reason why we're going to have 5 different charts is because if you come over here, we set n values to the number of elements in the vector n values is 5, and then we create a for loop and we create a histogram for each of the values of n values. So the first value that we have is n equals 1. So you can see you've got your normal distribution, which looks like a rectangle. Okay, so and then the next graph we have is n equals 2. And then again, the normal distribution, it is the distribution has begun to resemble a normal distribution. And then in n equals 5, again, the distribution is looking more like a normal distribution. And then for n equals 10 and n equals 30, you can see again that the distribution created from the samples resembles a normal distribution. So what that does is that demonstrates the central limit theorem. So now what we're going to do is we're going to compare sample statistics. But if you bear with me 1 second. Okay, sorry, thank you for bearing with me. We're going to set the seed at 1, 2, 3. So every time you run this cell, it's going to set the variables up to the same value. And now what we're going to do is we're going to create a skewed distribution, which is an exponential distribution. And we have already created a skewed distribution in this video, but we're going to do it again. So population becomes Rx, so that means random exponential distribution, brackets 100,000, comma, rate equals 1 divided by 5. So what that does is that gives you a mean of 5. And then we're going to draw repeated samples and compute equals 40. So num cells, it becomes 5,000. Num samples, it becomes 5,000, and that's the number of samples that we have used in this video already. Sample means becomes numeric, brackets, num samples. Sample medians equals numeric, brackets, num samples. And sample bears becomes numeric, brackets, num samples. And then we'll create a for loop for I1 to num samples. S becomes sample, brackets, population, comma, n, comma, replace equals true, And then sample means I becomes mean S. Sample medians I becomes median S. And sample vars I becomes var S. And so that's your for loop. So it's gonna for loop, it's gonna iterate from 1 to the number of samples. And so we've got 5,000 samples. So it's gonna iterate from 1 to 5,000, and it's going to take the mean, median, and variance of those samples every time. So now what we're going to do is we're going to plot the sampling distribution. Par brackets MF rho equals C brackets 1, 3. And then we're going to create a histogram of the sample means, a histogram of the sample medians, and a histogram of the sample vars. So for the sample means, it's going to be hist brackets, sample means bracket, break equal 40, comma, color equals sky blue, comma, frequency equals false, comma, main equals sampling distribution mean, comma, X lab equals sample mean. And then for the histogram for the medians, you've got hist brackets, sample medians, comma, breaks equals 40, comma, col equals light green, comma, frequency equals false, comma, main equals sampling distribution median, comma, X lab equals sample median. And then for this variance, you've got hist bracket sample vars, comma, breaks equals 40, comma, col equals salmon, comma, freaks equals false, comma, main equals sampling distribution variance, comma, X lab equals sample variance. And so what we've done is we have created 3 histograms. The 3 histograms that we have created are for the mean, the median, and the variance. Okay, so, and you can see that the distributions created are a little bit different. So the histogram for the mean, let's just see. The histogram for the mean is a little bit skewed on the right side. The histogram for the median is a little bit more skewed on the right side. And the histogram for the variance is a little bit more skewed on the right side. And so what I wanted to talk about was the mean, the median, and the variance. So your mean is you sum up all of the elements in the distribution, and then you divide those elements by the number of elements in the distribution, and that's going to give you your mean. The median is you take all of the elements in the distribution and you sort those elements, and the median is going to be the center element in that distribution. So if the number of elements in the distribution is odd, then what's going to happen is the median is going to be the center element. But if the number of elements in the distribution is even, then you're going to take the 2 center elements, you're going to add them together and divide them by 2, and that's your median. And your variance is your variance, and then it gives you a formula on how to compute the variance, which I don't know the formula by heart, unfortunately. So that concludes this video. And the next video, we're going to be talking about some more statistical topics in R. So I hope that you decide to watch it.